Welcome back, and here we are. In this video, we're going to talk about introductory networking, and you can take this room as Networks 101. So if you haven't studied networking before, you can just enroll in this room, or if you don't want to enroll, you can just, I'm trying here to summarize every task. So instead of going about this room and reading every single task, I'm going to try to summarize everything and solve the question so you get an idea about Networks 101. So as you can see, all of the networking material starts with Aussie model. So in a nutshell, we have the Aussie model, which consists of 7 layers. The 7 layers, as you can see, for every computer on the internet, you can apply the Aussie model. So for the sender of a packet and for the receiver of the packet, the Aussie model applies. So, but if we're talking about the sender, the Aussie model works from the top down, top, bottom, right? This direction. If you're talking about the receiver, you can receive the packets from here, often bottom up, right? Bottom up. So basically, the sender of the packet starts from the application layer. The receiver of the packet starts from the physical layer. So the application layer handles here where most of the protocols lie. For example, HTTP, FTP, SFTP, they lie in the application layer. So here, where do you create your packet? Your first packet is created at the application layer. Then the packet is passed down to the presentation layer. The presentation layer handles the encryption and the compression. Then it goes down to the session layer. The session layer handles the functionality, right, of the session established between the sender, which is you in this case, and the receiver. Make sure the session is live and make sure the session is maintained throughout the duration of the communication. Now, after the session layer makes sure that the session is live, it's the packets, as you can see, application presentation session. The packet here is called data. Everything is going on here called data, right? Then it is passed down to the transport layer. The transport layer here, we choose the protocol, whether it's TCP or UDP. And as all of you know, the TCP protocol is connection based, meaning that it makes sure that the connection is established and there is no loss of data. UDP is connectionless. It favors speed over accuracy. So here the protocol is chosen, TCP or UDP, and we can call the we can name the data here as packets. In the case of UDP, it's called datagrams. Then the packets or datagrams are passed to the network layer. Here, actually, I made a mistake. The packets are called in the network layer, not in the transport layer. So then it's passed to the network layer. Here, at the network layer, we are talking about the source IP and destination IP address. So here the packet is formed with the protocol, the application, and the source IP and destination IP address. Passed down data link layer. Data link layer here, we are forming the binaries, right? The packets are converted into binaries. So data link, we're talking about the source MAC address and the destination MAC address. Then the data is passed down here, or the binaries are passed to the physical layer here where the medium is defined. Most of the time it's Ethernet, could be other medium. So basically the medium is defined, let's say it's Ethernet, and then the binaries from data link layer are converted into signals, electronic signals. That is the process if you are the sender. And we call this process as the encapsulation, okay? The sender encapsulates the data. Now the receiver, on the other end, they receive the data from the physical layer. Here where the process of decapsulation starts. So all of the data that we have encapsulated on the sender side, now it will be decapsulated the other way around. It will be received as signals, binaries, packets, and then datagrams or the TCP data. And here we have the application session, presentation, and application. That's all about the Aussie model in a very brief way, very brief. So let's answer the question. So which layer would choose to send data over TCP or UDP? Of course, it is 4. As you can see, we count like that. 1, 2, 3, 4. Not from here, from here. 1, 2, 3, 4. Layer 4, which layer checks received packets to make sure that they haven't been corrupted. Now here the checksums are performed. It is are performed at the second layer, which is data link layer. In which layer would data be formatted in preparation for transmission? Of course, it is the data link layer. They will be converted to binaries. Which layer transmits and receives data? It's the first layer. As you can see, your data or everything exits from here and enters from here, whether you're the sender or the receiver. So when sending data over TCP, what would you call the bite-sized pieces of data? It's segments. In the case of UDP, it's called datagrams. Which layer would the FT protocol communicate with? Of course, it is the application layer. Since you can install FileZilla, for example, and transport data, you can call it the application layer. Which transport layer protocol would be best suited to transmit live video? So in live video, here, we don't care, we care about the accuracy, we care about the quality of the video, the image, but not as much as we care about the speed. So it favors UDP. That's why. That's about the OZ model. Now, encapsulation, actually, I have explained this when we were talking about the OZ model. So encapsulation briefly is the process of adding at every stage. As you can see here, there is a header added for every layer. Application layer adds a header, contains the application layer data. Presentation layer adds a header, which contains the presentation layer data. All the way down, as you can see, application, presentation, session, we are talking about data. Here, transport, it is determined whether it is segments in the case of TCP or UDP in the case of datagrams in the case of UDP. Network layer, as you can see, the segments or datagrams are converted into packets. Here we define the source and the destination IP. Data link layer, the header of data link layer defines or calls the data to be frames. Then we are talking about the bits. So how would you refer to data at layer 2 of the encapsulation process? Of course, layer 2 is data link layer and we call it frames. How would you refer to data at layer 4 of the encapsulation process? If the UDP protocol has been selected, we call this datagrams here. So what process would a computer perform on a received message? So we call that here, if you are the sender, the packets or the signals will enter from the physical layer, and then the process of decapsulation will occur. So it is the encapsulation, which is the only layer of the Aussie model to add a trailer during encapsulation. A trailer is for checking the corrupt data, which is data link layer. Does encapsulation provide an external protection? Of course. Yeah, that's for encapsulation. Now, the TCP/IP model. Actually, TCP/IP model and Aussie model, they are not the same, but they actually confer the same meaning, but in different way. So basically here, as you can see, the application layer in TCP/IP sums or combines application, presentation, and session all at once in the Aussie model. Transport stays the same. The network layer in the Aussie model is called Internet, and here data link and physical in the Aussie model is called network interface. All other things are the same except the naming or the aggregation. Let me say it like that. Now here we're talking about this TCP handshake. So let's get back here to the TCP model. When the data from the application, presentation, session are passed down to transport layer, as you can see, we here define whether we will use UDP and TCP. If we can use TCP, okay, what's going to happen? We're going to jump right here. Yes, here. So here what's going to happen? You are the sender, right? And you are at the transport layer. You will send the receiver a synchronization packet. You're going to ask the server that you want to establish a connection. If the server is up and running, I want to receive the connection. It's going to send you synchronization acknowledgement. It's like saying, yes, I am ready to send, I'm ready for your packet to be sent. Then you're going to send, oh, all right, that's okay, let's start. You're going to send acknowledgement. The three-way handshake works this way. After the three-way handshake is completed successfully without any loss, it's going to move on to network layer. Okay. Questions? So which model was introduced first? TCPIP is older than Aussie model. Which layer of the TCPIP model covers the functionality of the transport layer of the Aussie model? So basically, we said that the TCP/IP model uses the same naming with the Aussie model when it comes to the transport layer. So the answer is transport. Which layer of the TCP/IP model covers the functionality of the session layer of the Aussie model? We said that session layer, presentation layer, and application layer, they are grouped into one layer in the TCP/IP model called the application layer. The network interface layer of the TCP/IP model covers the functionality of two layers in the Aussie model. These layers are, as you can see, if you remember, the network interface TCP/IP model covers data link and physical in the Aussie model. Which layer of the TCP/IP model handles the functionality of the Aussie network layer? Remember, it's the internet. What kind of protocol is TCP? It's connection-based. Connection-based meaning that the TCP protocol favors the accuracy, right, and the stability of the connection. So that's why it's called connection-based. What's sync short for? Synchronize. What's the second step of the three-way handshake? So here, synchronize. Are you ready for the connection? Yes, I am ready. Synchronization acknowledgement. That's the second step. The short name abbreviation of acknowledgement is ACK. Okay. Now we get to the practical side, Wireshark. So here, let me go back to my machine and open Wireshark. It is open here. So here it applies the concept of what we have learned about the TCP/IP and the Aussie model on a packet. So as you can see, this is a packet here. The source IP is 172, and this is destination. And the application of the Aussie model here on the packets goes this way. So first we have the frame. As you can see, the first line here defines the physical layer, right? So basically here we received 81 bytes, right, on wire, 81 bytes captured. Next, we can see here the Ethernet, this is data link layer. It's saying that the medium is Ethernet, right? And here's the source MAC address and the destination MAC address. The third one is the Internet protocol. Why? Because it contains the source and the destination IP address. Here we are talking about the Internet layer in the TCP/IP model or the network layer in the Aussie model. As you can see, the Internet protocol is IPv4. User datagram protocol. Here we are talking about the transport layer. As you can see, the protocol is UTP, the source port and the destination port are defined. And the last one is the application layer. In the TCP/IP model, this one covers the application, presentation, and the session layer. That's the application of the Aussie model and TCP/IP model using Wireshark. Now, let's go back and answer the questions. Okay. So what is the protocol specified in the section of the request that is linked to the application layer of the Aussie? DNS, why? This is the data of the application layer, DNS protocol. Back. Which layer of the Aussie model does this section that shows the IP address? As you can see, without going back to Wireshark, the Aussie model that defines, or the Aussie model layer that contains the IP is the network layer. In the section of the request that links to the transport layer, which protocol is defined? It's asking it is UTP or TCP. As you can see, we saw it was user datagram protocol. Fairly easy. For what medium has this request been made? We can see the medium in the data link layer, which is here, Ethernet 2. Which layer of the Aussie model does this section that shows the number of bytes transferred? Of course, it's physical layer. Research can figure out what kind of address is shown in the layer linked to the data link layer. Without going back to Wireshark, you know that the addresses used in data link layer are the MAC addresses unique to every computer. Okay, Wireshark. Ping. Now, ping. All right. So before answering the questions, let's talk a bit about ping. You know how to use ping, right? So ping is a utility, networking utility used to make sure that the remote host is live. For example, I want to make sure that Google is live. I type ping Google. And when I receive the bytes from Google, means that google.com is live, up and running. Now, we can also use man ping to see the switches we can use with ping. For example, the switches that the questions center around are how to define interval, right, for the packets, how to define an interface if you have more than one interface, and how to define the internet protocol, which is whether it is IPv4 or IPv6. So use -4 for IPv4 and -6 for IPv6, and you define the packet size. So let's use an example for example. Let's say, for example, I want to sudo, or no sudo, ping -c. We define the number of packets, let's say 60 packets, right? Let me go back to my ping. So we use -c, as you can see, to define the number of packets, yes. So ping -c, let's say 80 packets, and we use the IPv4 and the interval with seconds to be every 10 seconds, and the host is google.com. So every 10 seconds, I am sending a request. As you can see, it waits for 10 seconds, then it sends the second request. Okay. So now answering the questions would become much easier. What command would you use to ping? That's very easy. And of course, one way to use ping is to determine the IP address of the host. So basically here, the IP of Google is this guy. That's how we define the IP. What switch lets you change the interval of send ping requests? We use -I. What switch would allow you to restrict requests to IPv4? We use -4. And this is for verbosity. This is very basic use of ping. Now Traceroute is used to know how many hops. Let's take an example. So we use Traceroute actually to determine how many hops and what they are when we send a packet from our computer to a target host. For example, I want to know what are the switches, the routers, the mediums that stand in the way when I send a packet from my computer to google.com. So I would say traceroute google.com. Show me the guys you are passing by when you go to google.com. So you can know that using traceroute. All right, these are the questions. We're gonna answer these, but I got some weird output. Okay, let me choose traceroute tryhackme.com. So 30 hops, as you can see. But I can't get the same output, right? The same one as the guy got here, right? So the output is a bit different from my output. All right, so let's do the traceroute actually. Now here, it is asking what switch would you use to specify an interface when using traceroute. You can know all the switches actually. Well, how? You just type man traceroute. Here you can see all the switches and the use cases for each one of them. So the ones that the questions have queried about are the protocol and whether we're going to use TCP or UDP. So here, as you can see, -T, we're saying that traceroute, hey, use TCP when making the request. And traceroute 6 for IPv6. And that's it. Of course, that's not all about traceroute, but that's a basic explanation of the use of traceroute. So basically here, as you can see from the illustration in TryHackMe, The guy has Traceroute, has followed the path it takes from his device all the way till it gets to Google, right? So you see the IP address of Google is here, the end of the request. And the guy started from here, the gateway, right? And between the gateway and the IP address of Google stands all of the routers, switches, network devices that stand in the way. These are, your ISP is one of these guys. So I guess the ISP is, let's check here, this is the gateway. And this is the ISP, I guess. This is the ISP here, right? And then we get some other servers all the way to google.com. So it's very good for troubleshooting. If you can't reach google.com and you want to know where is the hiccup along in the path, you can determine from Traceroute. In Windows, let's see Windows here, CMD. In Windows, we would use another tool, or the same tool, but actually different name, Traceroute, google.com. So in my case, as you can see, it starts with my router, asos.com. And here, the next step is, I guess, the DNS server, my DNS servers. Let's see what comes next. 62. Then we have my ISP. This is my ISP, by the way. Super online. And then we have some other hub. Next. Seems like this hub is on the same network. So we have the same network here. As you can see, the same subnet, 73.2.21. And now a different network. Again, different hub, but the same network with IP address ends with 205. Now again, different network. And you can determine what the IP address to which entity belongs, right? Using NSLOOKUP, for example. For example, I can type NSLOOKUP, for example, and this one. 10, 10, 1040, 148, 73. This is my non-existent domain. Can't find this. What about 2? Oh, okay, 2. Same. What about the 38, 211, 205? So it seems like my router cannot find this, right? So why? Maybe because this address doesn't exist in the recursive DNS servers of my ISP, so it tries to find them other way from the root DNS servers. Okay, anyway, that's about Traceroute. Now, whois? So all of you know whois, right? To determine and find the ownership of the domains. So I haven't solved this. Let's solve it together. So here we performed this on Facebook and we answered the questions. So let's perform that on Facebook. Here goes Facebook. Of course, you can bypass or you can hide your ownership details of the domain by using the privacy protection offered by the registrars. So you can hide most of this info with the privacy protection. But some domains choose not to do. So let's go back, and what is the registrant postal code for facebook.com? So you would look up here, find the postal code. So it is 94025. When was the facebook.com domain first registered? So we see the registration dates up here, creation date. 1997, 0329, here where Mark Zuckerberg had the revelation about Facebook. So this is the date. But we have to format the states according to TryHackMe answer format. Oh, no. DDMMYY. So it's up the other way around. DD Is this right? Yep. Perform a home search on Microsoft. Which city is the registrant based in? So let's perform now on Microsoft. What is that? Who am I? Microsoft.com. Did I make something wrong? Extra operand. Oh, I just typed something different. Who is Microsoft.com? Let's get up and find the city. So it is Redmond. What is the name of the golf course that is near the registrant address for Microsoft.com? So this is OSINT. What's the name of the golf course that is near the registrant address of Microsoft? So this one here, it is hinting about OSINT, means that we need to use Google about this or some other source. So I'm going to type Google. Or here, let's type golf course Microsoft. So let's what's up? City. Get mini golf club. Links master list of available courses. Let's see here. So all of these are courses, golf courses. It could be one of them, but we have to match this with near the registrant address. So registrant address is Redmond, WA. All right, so what will we type here? We'll get back and type Redmond golf course Microsoft. The best 10 golf near 1 Microsoft Way Redmond. Oh, we have many. So let's try this one by one. And this is correct. Okay. Next one. What is the registered technical email for Microsoft.com? Technical email. Tech email. It would be this one. Okay. That is for whose. Now, dig. Actually, dig is the tool that you would need the most when you troubleshoot networking tools. Why? Because dig here displays DNS information about any request, any server. For example, let's take an example. The syntax for dig is this way. For example, here I will clear and type dig, for example, google.com. So here I got the answer. Now the section that would matter the most is the answer section. The answer section reveals the domain that you have just queried, the time to live, and the IP address of google.com. And the query time, as you can see here, this is the server. What is the server? This is the server that we have asked, right, to give us the IP address of google.com, which is called the recursive server. The recursive server is the server or the first server, okay, your computer asks when it wants to get or retrieve the IP address of a domain name. This is the recursive server. Now the recursive server actually, normally it is a list of many servers that is maintained by your ISP. So your computer first, it looks in the DNS cache. Where is the IP of Google? If it doesn't find, it will ask the recursive servers list maintained in the ISP. If it is not in the recursive servers, it goes to the root name servers. Okay, and then to the top level, .com, .net, .uk, whatsoever. So for example, we know that Google DNS is 8888, right? So if we get back here, we see the questions. What is DNS short for? What is the first type of DNS server the computer would query when you search for a domain? We set this to recursive. These are the first line of DNS servers your computer would ask when it wants to retrieve the IP of a website. Remember this very carefully. Recursive comes first. Then we have the root. Then we have the top level ones. Then we have the authoritative. The authoritative name servers or the authoritative DNS servers are dedicated for every domain. What type of DNS server contains records specific to domain extensions? Okay, for domain extensions, as you can see, .uk, .com are called top-level domain. These come after the recursive. So if your query doesn't exist in the recursive, it then would ask the top level. The local cache is the first place it asks before it goes to the recursive one. Google runs two public DNS servers. Now, of course, you know the second IP of Google DNS. It is 8844. If a DNS query has a TTL of 24 hours, what number would the dig query show? Let's talk about the TTL. So if it gets back here and say, for example, dig google.com, and here we, for example, put at, forget about Facebook, Google, put Facebook, or TryHackMe. Let's see here. So we see here in the answer section, we got many entries. So let's explain them one by one. So answer section starts from here. As you can see, TryHackMe has 3 different IP addresses, 1, 2, 3. And 5 is the time to live. The time to live is the time your computer, uses to determine when it will ask the name servers again. So for example, in your computer now, the IP addresses of TryHackMe will be stored for 5 seconds. After 5 seconds, your computer will ask again the recursive servers, what is the IP address of TryHackMe? Now, here we get authority section. Again, we get authority section, and we have Cloudflare. And these are the authoritative DNS servers. As you can see, so it means that TryHackMe, right, their DNS records are contained in Cloudflare. Why? Because the authoritative DNS servers are Cloudflare. And the authoritative DNS servers contain the DNS records. Query time, 20 milliseconds, server, when, and message size. That's about dig. You can use dig to determine the authoritative DNS servers, the recursive ones, the IP address of the TryHackMe, the destination, and the TTL. Okay. So how do we calculate this? Here's saying a DNS query has a TTL of 24 hours. So, and we know that the TTL is counted or is calculated in seconds, which means you will convert the 24 hours into seconds. How? 24 times 60 will be in seconds, will be in minutes, and the amounts taken, for example, here, 24 hours times 60, 1,440 minutes, right? For 1,440 minutes times 60 for seconds yields 86,400. That's the answer in seconds. Time to live means that your computer will store, right, the IP address of the target server for 86,400 seconds, meaning 24 hours, one day. That's for dig. Further reading, nothing to answer here. So that is about the introductory networking. It was very brief. I tried to summarize as much as I could to save you time from going all over these and reading every word. So the next thing will be, let me get back here, CompTIA Pentest Plus. So network vulnerabilities, we finished this, and we have done this before. So we have network services, part 1, part 2. We're going to go over how to enumerate network services, and yeah, we have Active Directory left, and that's it about CompTIA Pentest Plus. I hope you liked this video, and see you in the next video.